So last time we showed that when you have a normal subgroup of a group, you can inherit the multiplication operation on the cosets of the subgroup from the big group. In this video, we're going to give that structure a name, and we're going to analyze this new structure a little bit. The collection of cosets of normal subgroup H in G is denoted G over H, or G mod H is the terminology that I'll probably use a lot for this. And the big result for this video is the following theorem. G mod H is a group under coset multiplication. And the proof of this is essentially just a little bit of a routine checking, just unraveling the definitions. So what do we know? In order to see something as a group, we need there to be an associative multiplication operation. And indeed, here, if I have HA and HB and HC, right, multiplying these two first, we saw how to define that last time. That is HA times HBC, and this is H of A, B, C, written out in, copious parentheses to make sure that we agree with what's going on here. Now we can use the normal associativity of the group to rewrite that as HABC. And then I break this back up. I need to scroll down just a pinch to HA dot HB dot HC. Okay, that's the first thing we need. The next thing we need is an identity element, neutral element. This is the coset of the identity, namely HE, or just H itself. And we know that that works because of essentially the previous discussion on cosets, right? The way cosets work is they essentially absorb anything that belongs to H. Well, H times HA is of course equal to HA. But if you want to see this written out in a little bit of detail, we can write this as HE times HA, or H of EA, or H of A, because E is the identity element of the group. Lastly, since we know that HE, or just H for short, is the identity element, then the inverses are also constructed from group element inverses. Written out, the inverse of HA will be defined to be HA inverse. And this is an inverse because HA inverse times HA is HA inverse times HA, or HA inverse A, or HE, or just H, which is what we just said is the neutral element of this construction. Had to do a little bit of squeezing there at the end. Okay, and that seems to be everything we need to prove to show that this is a group. So we've established the theorem. There should be one more thing that we should do for this video, which is the following. This is theorem 4 in this section. I don't think I wrote this at the beginning. No, I didn't. This is theorem number 3 of this section. And now we're going to look at theorem 4. G any group, H a normal subgroup of G, then there is a homomorphism G to G mod H. And so, in other words, we are showing that G mod H is a possible image of a homomorphism. And actually, what we'll do in the near future is show that every homomorphic image can be obtained in this way. But for now, one result at a time. So here's how we do this. In light of the previous discussion of coset multiplication not being well defined when when H is not normal, we saw in the homework, we had a question that that the number of cosets AH on the left was equal to the number of cosets HA on the right. And the idea was, or rather the naive idea, which doesn't work, was to send a coset AH to the corresponding coset HA. But there was a problem, which was the exact same problem that we ran into previously with cosets and functions, in this case, not being well defined when you try to do things with them. However, since I'm now assuming that we have a normal subgroup, now this idea will work. So what we do is we take some G in G and we send it to G capital H. Sorry, we're using right cosets in Pinter. So we send that to H capital G. And so now what I have to do is prove that this is a homomorphism. So to prove that something is a homomorphism, let's call this map phi. I need to prove that phi G1, G2 equals phi G1, phi G2. Over on the left, this is H G1, G2. And this is HG1 times HG2. But since H is normal, these two things are equal precisely because that is how coset multiplication works. And so there's actually nothing to check here. And this is a very special thing that happens in algebra sometimes, where sometimes it is very difficult to make something work or to say how a construction should go. But once you have the right notion, for us that being a normal subgroup, the proofs just write themselves because somehow the definition has been selected in this careful way that makes it so that the desirable property that you want just seems to happen all by itself. All right, at this point, I have been talking now for, again, almost 9 minutes. And so there's still more to say about this. In particular, I think the time has come for examples. But at the risk of making this video blow up too long, also, let's once again pause here and then let's use some real estate in the next round to, really get some familiarity with these quotient groups.